Good morning, good afternoon, good night, wherever you are in the world, and welcome to session 2, Renewable Nanomaterials as Films, Coatings, and Packaging Substrates. We have speakers in this session with some very interesting data and insight to report, and I'll get right to it because we only have 20 minutes for each speaker, so I want to give them as much time as possible. Our first speaker is Eva Pasquier from the Université Grenoble Alpes. Sounds like a mountain town to me. And Grenoble, a famous nanocellulose town. And she will talk about multi-layered films based on cellulose and chitin nanofibers for food packaging. And all these sessions, all the talks here are recorded. So let's please roll the film on the first talk.
Hello everyone, today I will present on bio-based multi-layered films based on cellulose and chitin nanofibers for food packaging application. This is part of my PhD that is held between LGP2 in France and Aalto University in Finland. So first, why do we want to improve food packaging today? One thing is the packaging we are using today are made from petroleum that has taken millions of years to be produced. What if we could produce the same packaging, but from trees that only take a few years to grow, or animal plant like hemp? Another thing is that the plastic that we are using today has a very low recycling rate. Today is around less than 10% in the US, compared to paper and cardboard that has a high recycling rate of around 70%. But the problem with paper and cardboard, it has some limitation, like it's not transparent, it has a low wet strength and also low oxygen and water vapor barrier properties. So how could we improve this? One way is to make multi-layers. So in a multi-layer material, you have different layers that have different functions. For example, for sealability, and then some barrier properties, and also some layers that are only there for adhesion. The most well-known multi-layer packaging is Tetra Pak. So it has, for example, paperboard as the main component that is there for the mechanical properties, and aluminium for the barrier and light barrier properties, and also several actually polyethylene layers. Some of them are there for the water barrier, but most of them are there only as a tie layer, so for adhesion purpose. So how we could reduce the number of layers and maybe increase the bio-based amount in this kind of material. What we have engineered is only based on bio-based materials. And the first component is cellulose nanofibers. It's known to have good oxygen barrier properties. Then we added some wax because it can form this continuous and non-porous layer that will have really good water vapor barrier properties. And then we wanted to have some lignin particles because it can increase the UV blocking property while keeping some transparency. And also it is antioxidant material. So this would form a multifunctional and high barrier material. And what we want to use to make it, so first cellulose nanofibers. As you all know, they can be made from wood. And we want to add some chitin nanofibers that are extracted from shrimp shells, because chitin has a positive surface charge, and this can bring better compatibility between components. Also, as additives, we want to use lignin from softwood and wax from cardinal battery. And this would make a 100% bio-based material, and we will use these components without any chemical modification. So the first thing is to produce the lignin particles. We use a solvent shifting method that is well known. So it consists of dissolving the lignin in a good solvent. Here it's acetone and water. And we pour it in on the solvent that is usually water. And by precipitation, it will form some lignin particles. Here you can see the TM image of lignin particles that were made in water as an anti-solvent. You can see that they are round-shaped. The size dispersion is quite high. You can see very big particles. And also they are aggregated. So to change this morphology and also the size distribution, we added some nanofibers to the anti-solvent. And this led to lignin particles with smaller size distribution. For example, here with the cellulose nanofibers, you can see that the particles are way smaller, and however, they are still aggregated. And when we added some Cation nanofibers, you can see here, the lignin particles are actually well dispersed on the nanofibers. So we have adhesion properties, and we wanted to look at how where the adhesion between these. So we look at the interaction, and for that we did some high-speed centrifugation of the suspension. So the lignin particles with CNF and the lignin particles with... Hello everyone, today I will present led to lignin particles with smaller size distribution. For example, here with the cellulose nanofibers, you can see that the particles are way smaller, and however, they are still aggregated. And when we added some Cation nanofibers, you can see here, the lignin particles are actually well dispersed on the nanofibers. So we have adhesion properties, and we wanted to look at how where the adhesion between these. So we look at the interaction, and for that we did some high-speed centrifugation of the suspension. So the lignin particles with CNF and the lignin particles with chitin fibers. And you can see here, for the CNF, you obtain the CNF in the sediment and the lignin particles in the supernatant because they are stable. And for the chitin nanofibers and lignin particles, the lignin particles were present in the sediment with the chitin nanofibers. So this is because we have electrostatic interactions between the lignin particles that are negatively charged and the chitin nanofibers that are positively charged. While for the cellulose, we have both components that are negatively charged, and this leads to electrostatic repulsion. So we kept the lignin particles and chitin nanofibers because we want to have good adhesion during the film making process so that we do not lose any lignin particles. Then we prepared some wax particle suspension. For that, we heated wax solution so that it melts in water, and then we did sonication. After that, we used fast cooling to freeze the morphology of the particles. So here we obtained particles that were not so round-shaped, but more wax, broken wax. And the size was around 360 nanometers. And then we also wanted to see if the presence of nanofibers would influence in a way the size of these particles. So we added nanofibers in the melted wax and did sonication. And here you can see that we also have a decrease in the size distribution. So we have more homogeneous suspension. So that was the particles preparation, and then we started to make the layers. So first I will present on the lignin particles-based layer, and then the wax-based layer, and then a few results on the multi-layers that we produced. So first, the lignin particles and chitin nanofibers. We use different amount of lignin particles in the films, and you can see that the transmittance, light transmittance decreases with increasing amount of lignin particles. But for all of them, we found that the lignin particles would block the UV completely. So this was very good. And only 9% was enough for UV blocking. So we kept this concentration. We also look at the antioxidant properties, and you could see that they increase with increasing lignin content, which was expected. Then we engineered the wax layer. For that, we use a sandwich method. So it consists of first filtration of the nanofibers. Then we filtrated the wax particles, and at the end we filtrated again some nanofibers on top. So we have the wax that is in between the two layers of CNF. And at the end we used a hot press so that we dry the film and also partially melt the wax particles so that it would make a continuous layer of wax. Then we look at the barrier properties against water vapor, because that was our goal. So we measured the water vapor transmission rate, and we compared it with the CNF alone. So both film had the same thickness so that it can be compared. And we did this measurement at 50 and 80% humidity to see the effect on the swelling of the nanofibers. Here you can see that we have a huge decrease in the water vapor transmission rate, around 2 orders of magnitude lower, which is really good. And even at high humidity, the water vapor transmission rate increases a bit, but it's still around 10, which is quite good. And then we compared to other films that we processed, but in a different way. So we did mix just the wax and the CNF together, but this didn't lead to any continuous layer. Then the wax amount was too low. And then we also did a top layer of wax, but this was less homogeneous than the sandwich layer. So you can see that the deviation was way higher. And if you compare to commercial plastic that are available right now, you can see that we are a bit above the petroleum-based plastic, but still compared, for example, to PLA, we're really below. And then we did some multi-layers. So for that, we used cellulose nanofibers as a base layer, and then some wax particles, and then the chitin nanofibers and lignin particles on top. So this corresponds to the sandwich film for the wax. And we also replaced one of the CNF by chitin nanofiber and lignin particles. So you can see that the films looks quite homogeneous. However, when we did the SEM cross-section, you can see that there is a big crack in the middle, and this happened during the preparation of the sample for ICM. But it means that the samples are quite brittle, and this is due to the wax layer in the middle. So one way to improve this would be to use the wax with the CNF, so that maybe we have some reinforcement from the CNF in the wax layer. And this is ongoing work, so we still need to do it. And also we need to check if we have conservation of the individual layer properties in this multi-layer. So to conclude, we have prepared different nanoparticle suspension with and without the addition of nanofibers, and we look at the differences in morphology and also size distribution. We also prepared some single layers first of lignin particles and chitin nanofibers, look at the UV shielding properties and antioxidant. Then we prepared this wax-based layer that showed really high water vapor barrier properties. And finally, we prepared this multi-layer. And however, it still needs optimization. So this is ongoing at the moment. And in the future, we also want to look at the upscaling of this process. So how can we increase the scale? And maybe we would do it by coating or spraying. With that, I would like to thank you for your attention, and also to thank everyone who participated in this project from both LGP2 and Aalto University. And please, if you have any question, don't hesitate. Thank you.
Thank you, Eva. Very interesting talk. And there are questions. What type of filtering media did you use for the preparation of the layers? Can you hear me okay?
Yeah. So you mean is it the media of filtration? Is it the suspension?
What sort of filter did you use?
The filters. Yeah, so they are like PVDF filters, and the size, the porosity is, I think it's 0.4 microns. Yeah.
Okay. And do you have let me see, what is the level of the oxygen barrier, the OTR, that you achieved?
Yeah, so that's actually we haven't done yet, but it's in ongoing. So yeah, that's the next step, because we want to compare also to the plastic with that. But yeah, it should be close at least to the CNF layer alone. So usually it's around 1 in micrometers, cubic centimeters per day. Yeah.
Okay. And do you have an estimate of how much by weight or thickness of the wax you had in the sandwich system? Obviously, the barrier property depends on the thickness of the wax.
Yeah, so as you seen on the SEM, it was not clear how thick was the wax, but I did calculation compared to the thickness with the film with and without wax, and so it should be around 3 microns in thickness, and it's 9% in weight of the total film. Yeah.
Okay, very good. And which layer do you think actually contributed more for the reduction in the water vapor transmission rate? The wax or the chitin lignin?
Yeah, so it's the wax layer because it's wax is known to be super hydrophobic, and here it's really the one we have done these trials to put the wax on top of the CNF or to mix it in the CNF and this sandwich, and it's really the sandwich that gave the better water vapor transmission rates. So yeah, that's coming from the wax.
Okay. And can you repulp the sandwiches?
Yeah, that's a very good, interesting question. I mean, it's like any, I guess, CNF film. So you can, yeah, I think the wax will go off quite easily because at the moment we have problem of adhesion actually between the wax layer and cellulose and chitin. So I think it will be easy to separate the wax from the other layers. And then it's like CNF film, equivalent to a CNF film.
Okay. And unfortunately, we are out of time. So we're going to have to move on. Thank you very much, Eva. Very interesting talk. If you continue to put your questions in the chat and list Eva's name, she can respond to them later. Session, but far from the least, is by Rajesh Kopolu from Abu Akademi University, which is, if I remember right, the only university in Finland that teaches in Swedish. So that's interesting to me anyway. And he's going to talk about multi-layer barrier paperboard based on nanocellulose and biodegradable thermoplastics. So let's roll the film for Rajesh, please.
Good evening, everyone. My name is Rajesh Kopolu. I'm a final year PhD student at Abu Akademi University. Today, I will be presenting the latest results from my research on multi-layer barrier paperboard based on nanocellulose and biodegradable thermoplastics. Let us start by looking into what a barrier packaging is made of. Most often, it contains multiple functional layers depending on the end use. For example, it can contain paper or paperboard for stability and strength, an aluminum foil for oxygen or gas barriers, and fossil fuel-based plastics such as polyethylene for liquid barrier adhesion layers and so on. And if you look at the global plastic production since 1950, we can see that a majority of the plastics produced are used only once, and with most of them being sent to landfills or incinerated after use. And a very small percentage, the one in green here, is actually recycled. And of the total share of plastics, 40% of the plastics produced are used for packaging. And if you look at the data in 2015 for plastic production and plastic waste generation for different sectors, we can see that the packaging is the largest sector and also has the largest waste generated. And recycling rates in 2000, according to 2007 data, EU has a recycling rate of about 42%, while the rest of the world has an average of less than 10%. And most of this ends up in landfills and eventually oceans. And also, if you look at the municipal solid waste that is predicted to reach over 2 billion tons by 2025, and most of it contains single-use plastics. So this poses an urgent need to replace fossil fuel-based plastics with bio-based and biodegradable alternatives. That brings to the objectives of this work, where we wanted to demonstrate a biodegradable multi-layer barrier packaging paperboard with properties comparable to state-of-the-art. So the concept is that we start with a pigment-coated baseboard and then have nanocellulose on top of it as for oxygen, oil, and grease barriers, and a thermoplastic layer on the top and bottom to protect it from moisture. And also, we wanted to produce this multi-layer paperboard using continuous roll-to-roll processes such as slot die and extrusion coating. And then we looked at the influence of nanocellulose type extrusion polymer type, and pigment additives and plasticizers on the resulting barrier properties. So let's start with nanocellulose. Almost everybody attending this conference has worked with nanocellulose at some point and are aware of all the promising properties that it gives. And the main use for nanocellulose, or main interest for nanocellulose in packaging, is due to its good barrier against oxygen. So without going too much into the details, I would just explain the different kinds of nanocelluloses that we used in this work, which are like two types. One is a microfibrillated cellulose from University of Maine. So this is pure mechanically produced with diameters between 20 to 60 nanometers. And then we have a second type, which is carboxymethylated cellulose nanofibrils produced at Rice, Sweden, and a diameters between 5 to 15 nanometers. Both of these are nanoscaled fibers, and we just used microfibrillated to just distinguish the coarser one from the finer one. And we have a TEM image to show the fiber structure here at the bottom. And then if you look at the figure to the right, we can see oxygen permeance and water vapor permeance plotted on Y and X axes respectively. And a lower value means higher barrier. So the red dots here, MFC and CNF, are the ones that are used in this work. And this is for a pure film. And like we all know that nanocellulose have very good oxygen barrier, but a rather poor water vapor barrier. And common polymers such as HDPE and LDPE that are used in packaging have good water vapor permeance, but rather low oxygen permeance. So the target here is to get as close to this red box as possible, which has both oxygen and water vapor permeances or good barrier properties. So the question is, can we get there with a multi-layer structure while keeping it biodegradable? And speaking of biodegradable, let's look into thermoplastics, or the plastics in general. So over 90% of the total mass of plastics produced are thermoplastics. And in this work, we used hot melt extrusion to process these into thin layers onto the paperboard. And the main advantage of using thermoplastics is their barrier against water vapor. And if you look at the figure to the right, it separates different kinds of thermoplastics into different categories. Based on their source, they can be fossil fuel based or bio-based, or based on their end life, they can be non-biodegradable or biodegradable. And the best thing would be to have a material that is both bio-based and biodegradable. So that would be the holy grail of using a barrier packaging. So in this work, we chose representative plastics or materials from each section. So we used LDPE as a reference from the mainstream plastics, and then we used Ecovio, which is a product, which is a commercial product blend of PLA and PBAT, and it has compostability certificates. And PBS is also a new type of novel bioplastic, which is also in the green zone here, which is also used as a reference, which is also used in this work. And all the three polymers are labeled as L, E, and P respectively from here on. So if we look at the sample setup, so we have a baseboard, which is pigment coated paperboard, about 200 GSM grammage. And then we coat a thin layer of cationic starch for to promote adhesion with nanocellulose layer, about 100 milligrams per square meter, done with reverse Gruyere coating. Then we have a slot die coating of nanocellulose. So as we said, two different kinds of nanocelluloses. One is MFC, done at 8 micrometer coating and labeled as M. And we wanted to see the influence of pigments on barrier properties. So we added hyperplaty kaolin into MFC and produced two additional coatings at 10% and 40% clay addition levels. They're labeled as M10C and M40C, similar thicknesses. And then coming to CNF coatings, we had the pure CNF coating at about 5.5 micrometers. And then we also wanted to see the influence of plasticizer on the barrier properties. So we used glycerol here at 2 and 10% addition levels, labeled as 2G and 10G at similar thicknesses. And both the nanocelluloses have a CMC 5% added as a rheology modifier. And then we take this nanocellulose coated paperboard and then apply an extrusion polymer on top of it, 3 polymers, LDPE, Ecovio, and PBS at different thicknesses. and then they are given a prefixes of L, E, and P respectively. And all coatings were done as roll-to-roll processes. A few LDPE samples were also backside coated with LDPE to protect MFC from moisture penetration from the pack. They are labeled as L and L. Yes. So coming to the coating process, the slot die coating was done at Obo Academy University using a mini pilot scale coater. It has a maximum speed of 50 meters per minute and can coat up to 300 millimeter wide webs. For this work, we have a custom fitting of slot die and coatings of 10 centimeter wide and 5 meters per minute line scale. And then this coated paperboard was then taken to Tampere University and coated, extrusion coated using their pilot scale coater, which can run at a maximum speed of 400 meters per minute and a maximum web width of 550 millimeters. For this work, we ran the machine at 700 meters per minute, and the samples were also corona treated to improve adhesion. So looking at SEM cross sections, here on the left, I have the cross sections for MFC containing multi-layer paperboard with LDPE, Ecovio, and PBS from top to bottom respectively. And one can see the various layers easily. So we have the baseboard, pigment coat, pigment surface, and MFC, and then LDPE, and here the other polymers respectively. And if we look down here, we see that PBS does not have a very good adhesion, and one can see the layer separating. And when we blend kaolin into MFC, it improves the adhesion with PBS, like you can see in the image below. Also, a plasma treatment or having ultra thin pigment coating on nanocellulose might also improve its adhesion to thermoplastics. So moving on to barrier properties, we look at water vapor barrier. So water vapor permeance was measured at two conditions, 23 degrees Celsius and 50% humidity, and 38 degrees Celsius and 90% humidity. So the blue one is at 50% humidity and the red is at 90%. So when we look at the just MFC and CNF coatings, we see like they do not have good barrier, or they have high permeance, and this is expected for all nanocellulose coatings. But then if you look at the water vapor permeance for extrusion coated samples, LDPE, Ecovio, and PBS, we see a very large reduction, like 95% reduction for LDPE and 72% reduction for Ecovio and PBS top layers. And we get similar values for multi-layer samples because it's the top layer that controls the water vapor permeance. And kaolin and glycerol addition did not show any difference in the water vapor permeance. Moving on to oxygen barrier, here we look at the influence of extrusion coating polymers, and the oxygen permeance was measured at 23 degrees Celsius and 50% relative humidity. Let us first start with the image on the top. So here we have a comparison of Petri dish films versus roll-to-roll coated nanocellulose samples. So compared to Petri dish films, we can see like the roll-to-roll coated films have a very high oxygen permeance. And also one thing to note that this is a logarithmic scale. So it actually has a 3 orders of magnitude higher permeance. So this is probably due to the extreme drying conditions in the roll-to-roll process that leads to cracks or defects in nanocellulose coated layer, and therefore a very high oxygen permeance compared to those of pure films. And also the value for the films is for the same thickness, so which is about 6 to 8 micrometers. So if you have a higher thickness nanocellulose films, they all obviously have very low oxygen permeance, less than 10 or even 1 if you go up to 20 microns. But then now moving to the figure on the bottom, interesting things start to happen. So here we have 3 sets for 3 different extrusion polymers, LDPE, Ecovio, and PBS. So the red one is for just the polymer, and then the blue is when they have MFC as a multi-layer structure, and then the green one is when they have CNF as a multi-layer structure. And one can see that the polymers, the thermoplastics as such, do not have any oxygen permeance or very high permeance. And then as soon as we have a multi-layer structure, the oxygen permeance falls down, and these values are very, very close to what we get for the pure films. So what is happening is during extrusion coating, molten polymer fills in cracks or defects in the nanocellulose layer, and therefore oxygen permeance values get better, and they show similar values to that of pure nanocellulose films, which is very promising. Now we look at the influence of oxygen barrier on of additives on oxygen barrier, and the test conditions are the same: 23 degrees Celsius and 50% humidity, and all measurements are for multi-layer coatings. So on the left we have a kaolin blended into MFC, and for 3 different polymer coatings on top. So as we go from 0 to 40%, one can see the barrier gets worse. But a 10% kaolin blend has a similar oxygen permeance to that of pure MFC coating. So one can say like a small percentage of pigment can be added to improve adhesion without compromising much on the oxygen barrier. And also there might be some applications which does not require a high enough oxygen barrier. So one can replace a little bit of nanocellulose with pigments and save expensive materials. And on the right, we have an influence of plasticizers such as glycerol on oxygen barrier. So we see as we add glycerol to nanocellulose, the oxygen permeance goes down. So it could be like the glycerol addition makes a flexible and uniform nanocellulose layer and therefore has better oxygen barrier. And actually, it is comparable to pure films at 0% humidity. And then moving on to influence of oxygen barrier as with respect to relative humidity and double-sided extrusion coating. So here we have 3 conditions: 23 degrees Celsius, 50% humidity, 75% humidity, and then 38 degrees and 90% humidity. And for MFC and LDPE coating, multi-layer structure in the red, and then the sandwich LDPE structure in blue. So oxygen barrier gets worse at higher temperatures and relative humidities. Backside extrusion coating protects nanocellulose to an extent, yet falls short of required values for certain applications. This is because water vapor might be seeping in through along the cross section. Sealing the cross section or sandwiching nanocellulose in between water impermeable layers might help improve the barrier a little bit, but still it is promising that a backside coating of LDPE protects the nanocellulose layer to an extent. Moving on to grease barrier. So we used an olive oil as the grease test, and then this was done at 40 degrees Celsius. Traditionally, grease barrier is done by putting the samples on a glass plate and then observed at regular intervals if the oil passed through or not. But this can be very challenging, especially when you have a white paper and then to see oil spots on the bottom of the paper. So what we did was we replaced the glass plate with a scanner that scans it at regular intervals, and then we take all the images and then process it through an imaging processing software that gives a image like on the top right as area penetrated as a function of time. And then we take the time for oil to penetrate 1% of the area as failure. And on the bottom, we can see for different coated samples, time to penetrate to 1% area. So MFC and CNF, they show very high variation, sensitive to coating defects, just like oxygen barrier. But and one can see like it can vary anywhere between like 50 hours all the way to 500 hours, where the test is actually terminated, and 500 hours is all approximately 1 month. Addition of clay negatively affects the grease barrier, and glycerol addition did not have any influence. And when we have extrusion coated samples, there was no failure even after 500 hours. And that was the duration of the test. Moving on to mineral oil barrier, we measured heptane vapor transmission rate at 23 degrees Celsius and 50% relative humidity. So pure nanocellulose coatings, Ecovio and PBS have 0 heptane vapor transmission rate. That is, no gas escapes even during the 48-hour test interval. Glycerol did not show any influence on heptane vapor, but clay addition to MFC reduces the barrier or increases the transmission rate. So the red one is just for the pure nanocellulose coating, and then the blue is when we have LDPE coating on top. LDPE as such does not have any barrier against heptane vapor, but as said before, it fills in any gaps and defects and improves the barrier a little bit. And even 10% clay here, for example, performs much better with LDPE coating on top. We also did kit tests for all the coatings, which gives a value from 0 to 12, with 12 being the higher barrier, and almost all the samples have a kit value of 12. So in summary, we use two continuous coating methods in tandem to produce a multi-layer barrier paperboard, by slot die coating of nanocellulose and followed by extrusion coating of thermoplastics to produce this paperboard. Extrusion coating helps offset any coating defects in nanocellulose layer and improves the overall barrier performance. Adding a small percentage of pigment into nanocellulose helps with adhesion with thermoplastics and also keeps the small percentage keeps the barrier properties intact. Plasticizers such as glycerol promotes uniform nanocellulose coating and therefore better barrier. And finally, sandwiching nanocellulose in between water impermeable layers could help oxygen barrier at higher humidities. And finally, I want to bring the attention back to this graph from the beginning of the slides. So the green ones are the ones samples from this work, and we did manage to come into the red box, which is the targeted ones. But unfortunately, these are only for LDPE coated samples, which are not biodegradable. But the promising part is the ones in the circle, which are EcoVio and PBS coated ones with MFC and nanocellulose. And we can see improvements in both oxygen barrier here with the CNF coated samples and in water vapor barrier for almost all of them, which move to the left. And this is also a reminder that the axes are in logarithmic scale. So this shift is actually quite a big change. And most importantly, the ones in the circles are 100% biodegradable. The samples in the circles are 100% biodegradable barrier paperboard. Yes. Thank you very much. This work has been done in collaboration between Åbo Academy University and Tampere University from Finland and Rice Research Institutes from Sweden. Thank you.
Thank you, Rajesh. Very good talk. And the chat is highly industrially relevant, of course. That's pretty sure that's your intention. You are able to put 8 grams per square meter of CNF on the board with a slot die. What was the speed and what was the maximum amount of CNF that can be applied here?
Well, the CNF that we got, the solids content was about 2%. So to get 8 GSM, I had to do a multi-layer coating there as well. So because it had so much water, the paperboard will not be able to take it. And also we didn't have that much drying capacity. So we did 4 grams and then 4 grams at a time. And the speeds were close to 5 meters per minute. Yeah.
Okay. Do you have ideas on how to continue this work to get in the box, fully in the box?
Yes, I think it's a bit difficult task because what I think is for anything to be biodegradable, it means that they should be all the groups, all the chemical structure should be accessible to fungus or bacteria or whatever that degrades it. And then it goes against the barrier property, because if you want it to degrade, then it shouldn't have barrier property. So I think it is just about finding the materials. I mean, if we can find some biomaterial that is good enough, it should be doable, I guess. Yeah.
Okay. And I had a dumb question. What is PEAT biopolymer?
PBAT, it is polybutylene adipate terephthalate or something. I think it was. It's based on fossil fuels as of now. And it's quite new or very less used. But I've seen some small companies that are popping up which have been working on this.
Okay.
Yeah.
And PBS is polybutyl succinate plus starch, right?
Yeah.
Great work. Have you compared lamination of polyethylene, for example, to the extrusion you did here?
No, we haven't done any lamination with that.
And another question, what are your thoughts on the use of plasma to make MFC films hydrophobic and so works as a better water vapor barrier?
Sorry, I didn't quite understand the question.
To use plasma
Yeah.
to make the MFC films more hydrophobic?
I don't know if it makes hydrophobic. I haven't seen any work or anywhere. I mean, it could work, but I don't know even if it is permanent, because most of the plasma or corona treatments, they are not very long lasting as well.
Yeah. All right. Well, it is now 45 until the hour, depending on what time zone you're in. And so it's time for us to stop with session 2. I think this has been a very good session. Good questions in the chat. Good presentations by all the presenters. Thank you all very much. Good job. And now I turn it back to Master Control for a break.